Welcome to our deep dive into the transport layer, the fourth layer of the OSI model and a core component of the Internet model. The transport layer is responsible for providing transparent data transfer between hosts, ensuring end-to-end control and the quality of service needed by applications. It sits between the network and application layers, acting as a bridge that manages data flow, reliability, and communication between processes on different systems. In this video, we'll explore the essential functions, protocols, and applications of the transport layer, setting the stage for a comprehensive understanding of how data moves reliably across networks. The transport layer offers several crucial services to ensure smooth communication between applications. These include process-to-process communication, addressing via port numbers, encapsulation and decapsulation of data, multiplexing and demultiplexing, flow control, error control, and congestion control. Each of these services plays a vital role in managing how data is packaged, transmitted, and received, ensuring that information reaches the correct application process without loss or duplication. Understanding these functions is key to grasping the transport layer's importance in network communication. One of the primary responsibilities of the transport layer is delivering data to the appropriate application process on host computers. This is achieved through process-to-process communication, where data from different applications is multiplexed into packets, each tagged with source and destination port numbers. These port numbers, combined with IP addresses, form a unique network socket, identifying the communication endpoints. This mechanism ensures that data sent from one application reaches the correct application on the receiving host, enabling seamless interactions between client and server processes. Port numbers are essential for distinguishing between multiple applications running on the same device. There are three main types: well-known ports 01023, registered ports 10244951, and ephemeral or dynamic ports 49150265535. Well-known ports are reserved for server processes, registered ports are not assigned or controlled, and ephemeral ports are temporary, typically used by client processes. This structured approach to port addressing allows multiple network applications to operate simultaneously without interference, ensuring organized and efficient communication. Encapsulation and decapsulation are fundamental processes in the transport layer. When sending data, the transport layer encapsulates application data by adding a header containing essential information like port numbers. At the receiving end, the transport layer decapsulates the packet, removing the header and delivering the data to the correct application process. This ensures that data is properly packaged for transmission and correctly interpreted upon arrival, maintaining the integrity and structure of the communication. Multiplexing and demultiplexing are techniques that allow multiple application processes to share the same network connection. At the sender's side, multiplexing combines data from different sources into a single stream, while at the receiver's side, demultiplexing separates the stream back into individual messages for the correct applications. This efficient handling of data streams ensures that network resources are used optimally and that each application receives its intended data without confusion. Flow control is vital for preventing a fast sender from overwhelming a slower receiver. The transport layer manages the rate of data transmission, allowing the receiver to control how much data it can handle at a time. This mechanism ensures that the receiving node is not flooded with more data than it can process, maintaining a smooth and stable communication flow between devices and preventing data loss due to buffer overflow. Error control at the transport layer involves detecting and correcting errors that may occur during data transmission. This includes discarding corrupted packets, tracking lost or duplicated packets, resending missing data, and buffering out-of-order packets until all data is correctly received. Error control ensures data integrity and reliability, making sure that the information sent is exactly what is received, even in the presence of network issues. Congestion control is crucial for maintaining network performance. When too many packets are sent into the network, congestion can occur, leading to packet loss and reduced throughput. The transport layer uses various mechanisms to either prevent congestion before it happens, open loop, or to manage it after it occurs, closed loop. These techniques help keep the network load within its capacity, ensuring efficient and reliable data transfer. Port numbers are 16-bit integers that uniquely identify processes on a host. They enable process-to-process communication and support multiplexing and demultiplexing at the transport layer. ICANN divides port numbers into three ranges: well-known ports for servers, registered ports for specific applications, and ephemeral ports for temporary client use. This system allows clients and servers to communicate efficiently, with each process assigned a unique port number for its data exchanges. Well-known ports 01023 are reserved for server processes and are universally recognized, ensuring clients know how to reach common services. Registered ports, 1024.49151, are not assigned or controlled, often used by specific applications. Ephemeral ports, 409152.65535, are temporary and typically used by client processes for short-lived connections. This structured approach to port allocation prevents conflicts and supports a wide range of network services. UDP is a simple, connectionless, and unreliable transport protocol. It adds process-to-process communication to the best effort service provided by IP, using minimal overhead. UDP does not guarantee delivery, order, or error correction, making it suitable for applications where speed is more critical than reliability. It is often used for small messages, real-time applications, and scenarios where the application layer can handle errors. UDP uses ports to identify server and client processes. Well-known UDP ports include 7 for Echo, 53 for DNS, and 161 for SNMP. Each port is associated with a message queue. Incoming messages are appended to the queue, and if the queue is full, messages are discarded. When an application reads a message, it is removed from the queue. This simple queuing mechanism supports efficient, lightweight communication for multiple processes. UDP datagram consists of a fixed-size 8-byte header and a variable-size data field. The header includes the source port, destination port, length, and checksum. The source and destination ports identify the sending and receiving processes, while the length field specifies the total datagram size. The checksum helps detect errors in the header and data, though its use is optional. This simple structure allows for fast, efficient data transmission. UDP provides process-to-process communication using socket addresses, and its connectionless nature means there is no setup or teardown of connections. Each datagram is independent, and there is no flow or error control beyond the basic checksum. Applications using UDP must handle any required reliability or error correction themselves, making UDP best suited for scenarios where speed and simplicity are prioritized over guaranteed delivery. UDP is widely used in applications where low latency is more important than reliability. Examples include network management protocols like SNMP, routing protocols like RIP, and real-time applications such as voice and video streaming. UDP is also suitable for multicasting and simple request-response protocols like TFTP, where the application can handle any necessary error or flow control. TCP is a reliable, connection-oriented, byte stream protocol that guarantees the in-order delivery of data. It supports full duplex communication, allowing data to flow in both directions simultaneously. TCP includes mechanisms for flow control, error control, and congestion control, making it suitable for applications where reliability and data integrity are critical. TCP's robust features ensure that data is delivered accurately and efficiently, even in complex network environments. TCP offers several key services: process-to-process communication using port numbers, stream delivery for continuous data flow, full duplex communication, and multiplexing/demultiplexing for multiple simultaneous connections. TCP's connection-oriented nature means that a logical connection is established before data transfer begins, ensuring that all data segments are delivered in order and without loss. Establishing a TCP connection involves a three-way handshake. First, the client sends a SYN segment with its initial sequence number. The server responds with a SYN ACK segment, acknowledging the client's sequence and providing its own. Finally, the client sends an ACK segment, confirming the server's sequence number. This process ensures both sides agree on initial parameters and are ready for reliable data transfer. Once a TCP connection is established, data can flow bidirectionally. Both client and server can send and receive data, with acknowledgements piggybacked on data segments. Connection termination can occur via a three-way close, where both sides close simultaneously, or a half close, where one side stops sending but continues to receive. This structured approach ensures orderly connection teardown and resource release. TCP segment consists of a header, 2060 bytes, and data. The header includes source and destination ports, sequence and acknowledgement numbers, header length, flags, window size, checksum, urgent pointer, and optional fields. Flags like SYN, ACK, FIN, and others control connection setup, data transfer, and termination. This detailed structure supports reliable, ordered, and controlled data delivery. TCP uses adaptive flow control, based on the sliding window mechanism, to guarantee reliable and ordered data delivery. The receiver advertises its window size, limiting how much unacknowledged data the sender can transmit. TCP maintains send and receive buffers, with pointers tracking acknowledged, sent, and written bytes. This system prevents buffer overflow and ensures smooth data flow between sender and receiver. Receive buffer in TCP holds data, even if it arrives out of order. Pointers track the last byte read, the next byte expected, and the last byte received. The advertised window reflects available buffer space, allowing the sender to adjust its transmission rate. If the application reads data slowly, the window shrinks, potentially reaching zero and pausing transmission until space becomes available again. Congestion control in TCP prevents network overload by adjusting the rate of data transmission. TCP maintains a congestion window for each connection, increasing or decreasing it based on network conditions. If the network is congested, the window shrinks, reducing the transmission rate. If the network is clear, the window grows, allowing more data to be sent. This dynamic adjustment helps maintain optimal throughput and network stability. TCP uses the AIMD algorithm to manage congestion. When the network is uncongested, the congestion window increases additively, allowing more data to be sent. If congestion is detected, typically by a timeout, the window size is halved, multiplicative decrease. This sawtooth pattern of window growth and reduction helps TCP adapt to changing network conditions, balancing throughput and congestion avoidance. Slow start mechanism in TCP rapidly increases the congestion window from a cold start. Initially, the window is set to 1 packet, doubling with each round-trip time as acknowledgements arrive. This exponential growth continues until a threshold is reached or congestion occurs, at which point the window growth slows. Slow start helps TCP quickly find the network's capacity without causing immediate congestion. TCP's fast retransmit and fast recovery mechanisms address packet loss without waiting for a timeout. When 3 duplicate acknowledgements are received, TCP assumes a packet is lost and retransmits it immediately. Fast recovery then uses the existing acknowledgements to continue sending data, avoiding a full slow start. This approach minimizes downtime and maintains higher throughput during transient network issues. Application layer is the topmost layer in the OSI and Internet models, providing network services directly to end users and applications. It encompasses protocols and services like the World Wide Web, WWW, email, file transfer, and remote login. The application layer enables user interaction with network resources, making it the gateway for all network-based activities. World Wide Web is a vast collection of interlinked documents and resources, accessible via browsers using URLs. Invented by Tim Berners-Lee, the web allows users to retrieve and view web pages stored on servers worldwide. Browsers communicate with web servers using HTTP, enabling seamless access to text, images, audio, and video content across the internet. Web browsers are client programs that allow users to interact with web servers. Each browser consists of a controller, client protocol, and interpreter. The controller manages user input and document access, while the interpreter displays content. Servers store web pages and respond to browser requests, sending the required files over established TCP connections. This client-server model underpins the entire web experience. URL is a standardized way to specify the location of resources on the internet. It consists of 4 parts: protocol, such as HTTP or FTP, host computer, optional port number, and path to the resource. URLs enable browsers and other clients to locate and retrieve documents from servers, forming the backbone of web navigation and resource access. Architecture of the World Wide Web is layered, starting with identifiers and character sets like URI and Unicode, followed by syntax XML, data interchange RDF, taxonomies RDFS, ontologies OWL, rules RAF, SWRL, proof cryptography, and finally user interface and applications. Each layer adds functionality, supporting the complex web of data and services available online. HTTP is the protocol that governs communication between web browsers and servers. It operates on a request-response model, where clients send requests for resources and servers respond with the requested data. HTTP messages consist of a start line, headers, and an optional message body. This protocol enables the dynamic, interactive nature of the web, supporting everything from simple page loads to complex web applications. HTTP request includes a request line, method, resource, HTTP version, headers, and an optional body. Common methods are GET and head. The server responds with a status line, HTTP version, status code, reason, headers, and a message body. Status codes indicate the result, such as 200 for success or 404 for not found. This structured exchange ensures clear communication between clients and servers. URIs are character strings that uniquely identify resources on the internet. They can represent documents, images, services, or even abstract entities. While URLs are a type of URI used for locating resources, not all URIs are URLs. This distinction allows for flexible identification and referencing of resources, supporting a wide range of internet applications and services. Mail is one of the most popular internet services. The user agent, UA, is the software that helps users compose, read, reply to, and forward messages. UAs manage mailboxes, providing inbox and outbox functionality. There are command-driven and GUI-based UAs, with modern examples including Outlook and Eudora. This architecture streamlines the process of sending and receiving electronic messages. User agents provide templates for composing messages, tools for reading incoming mail, and features for replying, forwarding, and managing mailboxes. Each email includes fields like sender, subject, and status. UAs help users organize their messages, making electronic communication efficient and user-friendly. Send an email. The user agent creates a message with an envelope and content. The local part of the address specifies the user's mailbox, while the domain name identifies the mail server. Emails are stored in the inbox until read and in the outbox until deleted. This system ensures reliable delivery and easy retrieval of electronic messages. Telnet is a client-server program that allows users to log into remote computers and access application programs as if they were local. It supports both local and remote logins, transforming user keystrokes into a universal character set for transmission. At the remote site, Telnet delivers commands to the operating system, enabling remote application access and control. Local login involves interacting with the operating system directly on your computer, while remote login uses Telnet to access applications on a distant machine. Telnet transforms local keystrokes into network virtual terminal characters, which are then interpreted by the remote system. This process allows users to control remote applications as if they were sitting at the remote computer. DNS is the Internet's phonebook, translating human-friendly domain names into IP addresses. It uses a distributed database spread across multiple servers, allowing clients and servers to communicate efficiently. DNS replaced the old host's TXT file system, enabling scalable and decentralized management of domain-to-IP mappings for the ever-growing Internet. DNS uses a hierarchical namespace, where names are structured in parts representing organization, department, and more. This allows decentralized control and avoids ambiguity. In contrast, a flat namespace assigns names without structure, which is impractical for large systems. The hierarchical model supports efficient, scalable, and conflict-free naming across the global Internet. Internet's DNS is divided into generic domains, like com, org, country domains, like in, UK, and inverse domains for address-to-name mapping. Generic domains categorize hosts by function, country domains by location, and inverse domains support reverse lookups. This structure enables efficient, organized, and flexible management of Internet addresses and names. Country domains use two-letter abbreviations to represent nations, such as O for Australia or IN for India. Inverse domains map IP addresses back to host names, supporting reverse lookups and authorization checks. This dual approach ensures both geographical organization and robust address-to-name mapping across the Internet. In this video, we explored the transport layer's vital role in network communication, covering its core functions, protocols like UDP and TCP, and their mechanisms for flow, error, and congestion control. We also examined application layer protocols, including HTTP, email, Telnet, and DNS, understanding how they enable seamless user experiences on the Internet. Mastery of these concepts is essential for anyone looking to understand or work with modern computer networks.